For most of human history, the understanding of what the world actually looked like was limited to whatever the eye could see. I mean, we know a lot now, but imagine living in a time where the idea of space doesn't exist, having no idea where you actually are or what the world looks like. People would look to religions and their own beliefs to try to make sense of everything, which is now known as Mythic cosmology. This era stretches broadly from prehistory through the first civilizations, roughly before 1500 BC. The landscape looked flat in every direction, and the sky was arched overhead in a dome that would rise and fall each day. Under these conditions, it was straightforward to think of a flat land surrounded by water or darkness, which was covered by a solid sky, something that looks like half a sphere. In this worldview, dramatic and unpredictable events like lightning, storms, and especially eclipses were explained through the intention of a higher power, which is where religions came in. If something powerful happened, like the sun disappearing, clearly someone powerful must have caused it. This reasoning shaped the early worldview as much as it shaped some early religions. And whatever forces governed the weather were also assumed to govern human fortune, which is why a lot of older religions were all about trying to please this power. These were all myths without any evidence, but were the only explanations for events that lacked obvious causes, and so they stayed. But as people traveled farther for trade and exploration, more contradictions showed up that were hard to ignore. By the 2nd millennium BC, sailors already knew that distant ships disappeared hull first, not all at once. Travelers realized that stars changed with latitude, meaning constellations visible in one region would disappear in another and weren't the same. During lunar eclipses, Earth's shadow on the moon was always curved no matter how the eclipse occurred. These observations made it more obvious that we live in a world far larger and more complex than the dome idea could explain. This didn't dissipate the old worldview immediately, but allowed for the first major scientific milestone of cosmology, all due to Greek natural philosophy. Between roughly 600 and 300 BC, some of the smartest Greek thinkers tried to find natural explanations based on geometry and observation rather than just creating myths. This period produced the earliest evidence-based cosmology, including the idea of a spherical Earth. Thinkers like Pythagoras and later Aristotle argued that a sphere was the most harmonious shape and that Earth must take this form because its shadow on the moon was always curved. Travelers had already shown that different stars rose and set at different latitudes, and a spherical Earth made this and all other observations perfectly logical. This period introduced a second major idea, that all planets, also known as heavens, must move in perfect circles. It was already assumed that other planets existed, with the word planet originating from the Greek term for wandering star, as well as the names of the planets themselves, like Jupiter. They believed that these were made of a special, unchanging substance which would rotate around the Earth in a perfect spherical path. Earth itself was motionless at the center of the universe because it had no natural direction to move. These beliefs were grounded in reasoning that made sense at the time, such as the idea of an existing heaven and us being at the center of the universe. But even in this era, deeper observations would contradict this model. Planets would move through the sky in irregular paths, sometimes reversing directions. To account for this while preserving the concept of perfect circles, Greek astronomers introduced epicycles, small circles whose centers moved along larger ones, the same way how Moon orbits Earth, which itself orbits the Sun. This of course ended up increasing the geometric complexity, which required something a bit more elaborate and smart to understand fully. And so the next milestone was Ptolemaic geocentrism. Claudius Ptolemy built the most advanced geocentric model, described in his book titled Almagest. His system placed Earth immobile at the center and used these epicycles and other new terms to try and match the observed paths of planets, which included the Sun. This model was not physically accurate, but it provided highly accurate mathematical predictions of where the planets would be moving to. And for over 1,000 years, the Ptolemaic system guided navigation, astrology, calendar making, and general astronomy across Europe, the Middle East, and North America. Due to this model becoming so widespread, observational precision also increased, especially through the work of Islamic astronomers from the 9th to the 14th centuries. This, however, naturally made the model demand more and more adjustments. Lots of little things, but mainly the fact that the motions weren't fully uniform and still had imperfections and unpredictable movements. And so the more complex people tried to get, the more of a mismatch they found between the model's assumptions and the structure of the planets themselves, which again they called heavens. By the Renaissance, the Ptolemaic system was accurate but not good enough anymore, precisely the kind of situation that causes a paradigm shift. That shift began with heliocentrism, introduced by Nicholas Copernicus around 1543, marking the next major milestone. Copernicus simply proposed that the Earth was just another planet orbiting the Sun. This simple change dramatically simplified the explanation for why planets would sometimes move backwards in retrograde motion. What had previously required complex math and machinery became naturally obvious once you considered that Earth and the planets moved around a central sun. Still, though, Copernicus held onto the now ancient assumption that planets must travel in perfect circles. Because of this, his model still required some tweaks and new rules to match their observations. But the idea was undoubtedly revolutionary, and people began looking for a superior predictive system with this new knowledge. The change came through the work of Tycho Brahe and Johannes Kepler at the beginning of the 17th century. Brahe's detailed observations, taken over decades, provided a new and very interesting set of data. When Kepler tried to fit Mars's motion using circles, the results failed by small margins, meaning that the model wasn't as accurate as it needed to be. Instead of adjusting the data or adding more circles, Kepler decided to abandon the concept of circular perfection altogether. He discovered that planets moved the way we know now, called elliptical orbits, which was the end to the 2000-year circle idea. This insight, part of the milestone called Keplerian planetary mechanics, described planetary motion with striking accuracy, even though he lacked a physical explanation for why they moved this way. Around the same time, in 1609, Galileo Galilei made improvements to the telescope to see the planets up close for himself. He saw mountains on the moon, moons orbiting Jupiter, and the full set of phases of Venus. These were incredibly important observations which put a total end to the idea that everything circled Earth and showed that the heavens were made of matter like Earth and not some celestial substance. Galileo also attempted to argue that tides proved Earth's motion, a claim we now know was incorrect. So figuring out the physics behind everything was their next step. And that came from Isaac Newton. In 1687, he introduced the law of universal gravitation and the free laws of motion, showing that Kepler's elliptical orbits were caused by a force acting between two masses. Newton effectively unified the planets and the Earth into a single system, which showed that the rules of the universe weren't just about glazing Earth. This achievement effectively ended the Ptolemaic era completely and established the Newtonian worldview as the next major milestone, often referred to as classical mechanics. For the next 2 centuries, Newton's framework explained everything from falling objects to planetary orbits. But beginning in the late 19th century, issues with the model started to show up. Mercury's orbit moved slightly more than Newtonian gravity allowed. The speed of light also appeared constant despite the observer's motion, not something that classical physics allowed to happen. And instruments became precise enough that these small contradictions could no longer be ignored. In 1905, Einstein introduced special relativity, the next milestone, something you all likely know about, which was about showing that measurements of time and distance depend on relative motion. A decade later, he proposed general relativity, visualizing gravity as a curvature in spacetime, which explained Mercury's orbit, and also predicted gravitational bending of starlight, which was later confirmed in 1919. All of this leads into a consideration of what the universe actually is. In the 1920s, Edwin Hubble observed that distant galaxies were receding, with farther galaxies moving faster. This meant that the universe was expanding and debunked Einstein's earlier belief in a static space. The idea of a dynamic universe became the next milestone, today known as physical cosmology. The next major milestone emerged in the mid-20th century with the establishment of the Big Bang model. Astronomers debated whether the universe had expanded from a hot, dense state or was just eternally steady. In 1965, it was actually discovered that there was a slight constant hiss coming from all sides of space, which was later found to be cosmic microwave background radiation, a predicted remnant of the early universe, which for now settled the debate in favor of the Big Bang. From the 1970s and onward, observations of how galaxies rotated and clustered didn't make sense when looking at their visible matter and gravity. This led to the concept of dark matter, forming the milestone of the dark matter paradigm. Later measurements of the cosmic microwave background confirmed that most of the universe's matter must be dark matter, which is invisible and non-atomic, explaining why galaxies with seemingly low mass were able to be held up with gravity. In the 1980s, the idea of cosmic inflation was discovered about a rapid expansion in the first fraction of a second after the Big Bang. This solved problems the Big Bang model alone could not, such as the apparent uniformity of regions that should have never interacted. In 1998, observations of distant supernovas showed that the universe's expansion was actually accelerating. This led to the recent concept of dark energy, a mysterious theoretical form of energy that counteracts gravity to push the universe further, which is all that's currently known about it. This combination of dark matter, dark energy, and the Big Bang model formed the standard model of cosmology known as the Lambda Cold Dark Matter Model, or CDM, which is the current milestone we're living through today. And it's the best currently available framework, describing a universe that's 13.8 billion years old, full of components we cannot yet directly observe. And just as before, it faces new contradictions. Different methods of measuring the expansion rate, called the Hubble tension, are now giving conflicting results. Experiments searching for dark matter particles have repeatedly come up empty, and the true nature of dark energy still remains unknown, where it comes from and why it accelerates the growth of the universe. And to remind you of everything we've talked about in this video, Mythic cosmology ended under observations from long-distance travel, Greek natural philosophy ended due to planetary irregularities, Ptolemaic geocentrism ended when too many epicycles were needed to preserve perfect circles, and Newtonian mechanics ended due to inconsistencies in light speed and gravity. And now, the current CDM model itself is showing similar signs of reaching its limits, meaning that in the next few decades, we may just have a repeat of history and discover something about the universe, or perhaps existence itself, that makes it much more grand and also comprehensible. But I'm curious to know what you think, so leave a comment about what the most interesting thing in this video was, and thank you for watching.